I'm Vanya. In previous videos, we looked into the power-saving features of narrowband IoT and Cat-M technologies, how to set them, and how they can be used to lower the power consumption of your Internet of Things device. Today, we're looking into 3 additional things that can have a major impact on your current consumption. Those are network registration, coverage, and the choice of protocols. And to guide us on this topic, we have Marcus from Thales. Hi, Marcus.
Hi, Vanya.
So, Marcus, how important is it to consider the impact of network registration, coverage, and protocols on the overall power consumption?
This highly depends on the use case, which is valid for your device, and of course for the network which is used. Every network has different conditions, and depending on your device activity, these are the main factors which are related to power consumption. As in 2G, 3G, and 4G, the LPWAN technologies can use different protocols and of course different security levels, and depending on your connection to the network, the internet connection to the servers, for example, you will have a different power consumption.
So let's start with the network registration. We know that different operators have different settings, which means that a device may not be able to maximize, or in some cases not even use some of the low power features. How does the network registration work, and what impact can it have on the power consumption?
Registration part could be quite complex, and this of course is quite important for your power consumption. There are so many frequency bands available that the scanning of all bands can take some time. Assuming we have a static device which is not moving at all, this would be the best condition, because this device will always try to register to the same cell on the same network, and this will go quite well. But as soon as devices are moving and have to scan the available cells all the time, this will have a quite big impact on your power consumption. I prepared an example of an initial network scan with a fresh SIM card, where the device is reading the content of the SIM card and then tries to find its home PLMN. So after startup, it will scan all enabled networks. In this case, only 2 bands have been enabled, so band 8 and 20. And problem is that many MNOs sell SIM cards which act in roaming mode, which has a big advantage for the MNO. You can use the SIM card all over Europe, for example. But the disadvantage is that the device is trying to find its home PLMN, which never will be found. And therefore, the scan is quite long. As we can see here, after our start, the scan is 1 minute and 20 seconds with an average power consumption of nearly 60 milliamp. This will be done in the automatic mode of the devices, which is described in 3GPP standards. One way to get around this is to manually set the network which the device should register to. So here, for example, I have my startup, and then I say the device to register to 26202 network, for example. And here we have our registration done, which finally is only 9 seconds. As you can imagine, of course, in 9 seconds, you will not consume so much energy as in 1 minute and 20 seconds. But this is mainly for the fact that the cell or the device did not have a cell before. So if the device just tries to reattach to a known cell, this is my third example, it will be even faster. As we can see here, in 4 seconds, the device will reattach to a known cell, which is a valid use case, for example, for all static devices. So any smart meter, for example, will not move. And as soon as the smart meter has found its cell and wakes up after, for example, a PSM period, it will just try to reattach to the last known cell first and to the last known network. And this is quite fast then, and of course the best solution we can have with an average of 25 milliamp only for 4 seconds. So this is quite fast and usable. Here's an example of NB-IoT network in Germany. We visualized a little bit the number of bands to scan and the scan time and the consumed energy during this time. And as we can see, it really makes sense to reduce the number of bands to be scanned to save power. But of course, everything depends on the use case. For a static device, it is perfect to reduce the number of bands because it will not move, no new bands, and using PSM and EDRX will be the perfect solution to save the power. But let's assume we've got a bicycle tracking bicycles in Amsterdam. This device will turn on once a week. Every week, the bicycle will be on a different place, and therefore the scan has to be completely new. And if we scan 20 networks and 20 bands, for example, this will really exhaust our battery. So limiting the number of bands and maybe a manual provider selection would be the best for such a use case.
How about the bicycle? If, let's say, assume that it's actually out of the city, out of the coverage.
NB-IoT and CAT-AM offer anyway an extended coverage where the device is doing retransmit of the data to come over these bad coverage scenarios. But depending on the protocol behind, retransmit may be confusing for the protocol, or maybe cause additional retransmissions, which cause more energy consumption finally. But finally, as in our EXS82 module, there would be the possibility, for example, to do a fallback to 2G, where we have the best coverage, I think, worldwide. But to come over this, a state machine in the device should handle this situation, should check the network status, or if the server side could be reached, and if not, do a fallback to 3G, and finally return to the power-saving technologies like NB-IoT or CAT-AM.
But not all modules have a fallback to 2G, since they don't necessarily have the radio for 2G, right?
Yes, this is an option. So as mentioned, our EXS82 module has the possibility to do a fallback to 2G. But I will show you the difference exactly here in this OT recording. Here we see our power consumption for 2G startup, registering to the cell, getting an IP address till a shutdown. And this is an overall power consumption of 1 milliwatt per hour. And if I now show you the NB-IoT part, where I have done exactly the same. So starting up, registering until I've got an IP and doing the shutdown, I will end up with 700 microwatt only. So there's a big difference between these technologies, and finally should always go back to the low power technologies.
Let's go into the kind of third part and the different protocols. It will be really interesting if you can show us how the data can be transmitted and what are the differences in power consumption that we can see when using different protocols.
Basically, every module offers a different set of protocols. Let's have a quick overview. For the different protocols, we have to find the balance between reliability, speed, and security, and finally power consumption. For example, UDP protocol, I do not have the guarantee that the packet will reach its destination. It's not connection oriented. But TCP, for example, is a connection oriented protocol, and the protocol itself will take care that every packet will reach the destination. If one packet is lost, for example, it has to be resent. And then, of course, there are higher level protocols like MQTT or HTTP, which are on top of TCP. Of course, they need the same mechanisms as TCP and add an additional overhead for their protocol part. So a lot of traffic and therefore higher power consumption. And finally, the topping is security, where you have to do handshakes and key exchanges and cryptographic operations on the device, which consume additional power. I've prepared a scenario where I used a static ENS22 NB-IoT module, and I always send the same amount of data, 40 bytes of data, a string and a number and a timestamp, just to represent, for example, a smart meter use case. And this I've done with different protocols to see how big is the impact from power consumption point of view. So I did some pre-recordings to shorten this a little bit, but let us do one live recording. And I wake up my module, and I've prepared a UDP socket onto my server, and I'm listening on that server port to see my final data, and I've got a TCP dump running as well. So I will just open the UDP socket, and as soon as the connection is open, I can send my 40 bytes of data, and then I will close my socket. And now the module is showing me that it's available to go into sleep again. And here I can stop my recording, because this is exactly the scenario I've done with the other protocols as well. As we can see here, I received one UDP packet on my server, and I always measure the time from where the module is ready to go to sleep again to the beginning of opening the socket. So with every protocol, I was measuring this time frame. So sometimes, of course, I'm a little bit faster. Sometimes I've been a little bit slower. The part at the beginning could be minimized a little bit. But anyway, we've got an overall power consumption of 480 microwatt for sending a UDP packet with 40 bytes of data. If I now go to TCP, for example, I've got exactly the same scenario. And as TCP has to send much more packets because there's an synchronization and acknowledges for each packet, and in NB-IoT it could happen that the packets have to be resent. We've got a longer period of activity and a higher power consumption with which is around 850 microwatt per hour. Okay, this was UDP and TCP. If I now go to make the same amount of data with an HTTP post to a server, I'm just marking it. We can see here, this is the HTTP part. It will be around 1 milliwatt per hour. So again, higher than in TCP. Let us check MQTT, which is quite often used protocol for NB-IoT. My MQTT connection will need 1 milliwatt per hour as well. So there's not such a big difference to HTTP, for example. And if I now go into security parts, for example, I use TLS, so a TCP connection which is secure. We see a much higher power consumption. Of course, there's a need to do the crypto part, and there's a longer handshake as well. It is possible to make UDP secure as well. This is called DTLS, and DTLS needs a high amount of power. It's about 1.8 milliwatt per hour. So main reason is here the security part, so the handshake and the key exchange mechanisms as well. I can make it a little bit simpler if I use a pre-shared key, the so-called PSK. With TCP and PSK, I go down a little bit to 1.1 milliwatt per hour, and the same is possible with DTLS, so secure UDP. This is around the same amount of power which I need to set up this DTLS connection. The difference is that a pre-shared key, the key which is used to crypt, is known on both sides already, and therefore we do not need so much energy and much less packets to be sent to get the crypto part up and running. Finally, I made a test with non-IP traffic, which is, as the name says, not using the IP protocol as a transport layer. So with non-IP, we just send our 40 bytes of data, and it is sent within the control channel of the mobile network, and the power consumption is going down to 320 microwatt. So this is definitely from power consumption point of view, the best solution.
There is an obvious difference in power consumption between these protocols. So let's look at the summary, and you prepared a good table for us to check that.
Yes, so I made a summary in this small table. As we can see, the power consumptions I just mentioned, which I have measured, but I really like the amount of IP packets and especially the amount of bytes which are finally sent to transport our 40 byte of data string. As already mentioned, for non-IP, only 40 bytes of data are transferred. For UDP, this is the amount is already doubled. And as you can see, if you use a TLS or DTLS connection, it's more than 1,000 times of the initial byte size is needed to transfer these 40 bytes of data. And the non-IP traffic is quite interesting. It consumes the fewest energy, as I said, but how is it done? So how will you get the data finally? Because non-IP will not be transferred into the internet because internet protocol is missing. So this data is finally terminating in the network of the mobile operator. The mobile operator will offer their customers different ways to access this data. Maybe they push the data to an internet server, or they offer a kind of web GUI where you can pull the data. But this push and pull doesn't affect your power consumption anymore, because this is on the network side, and so this is really the best solution from power consumption point of view for the device. But of course, the MNO, they offer this as a service, and you might have to pay something for this service to get a non-IP data connection.
So as a final note to summarize, network registration, coverage, and the choice of protocol can have major impact on the power consumption. In all of three cases, you need to really know your application and user case really well, and you can pick a really good path and get to this lowest current consumption. But it can come with the cost of having a fallback or having to have a fallback technology or additional network costs, right?
Yes, it's indeed quite important to understand every single part of the application and what constraints and opportunities each solution might have. And so testing the product during development is the key.
Yes, the testing is the key. Thank you, Marcus. And thank you all for watching. If you like this content, please like and subscribe to this channel. Until next time, thank you very much. Bye-bye.